The VOP16 is a great sensor. It's got 40 degrees field of view. For most applications, this is fine, but for mapping caves, this is a real constraint. The fix is conceptually pretty simple. If we've got the 40-degree field of view from the sensor and we rotate it around an extra axis, we can get a full spherical coverage of the area around us. The tricky part is doing it in a way that is mechanically reliable, electronically stable, and accurate enough for the point cloud deskewing and SLAM algorithms to make use of the data. In this video, I'm going to walk you through what I did to build this rotating platform and how it will capture a full volumetric scan of everything around it. So this right here is the original design, just kind of minimum viable proof of concept kind of deal. So initially used a 3/4 inch aluminum shaft with, which I thought was pretty funny, 3D printed bearings. Check these out. I just used steel BBs and pressed it together. It worked really well for proof of concept and kind of making sure that this could work. But we ended up moving to this, which is a lot more refined. So I just got these ball bearings. They've got a 2-inch OD, 1-inch ID. Fits right over the shaft. I say fits right over, I actually had to press them in with a big hammer and a socket. Then we've got the gear here, 60-tooth gear, which is also, all of this is just pressed on. There's not a lot of friction in the bearing, so it can still spin freely. So same with the cup that the sensor sits in. It also is just pressed on. I did learn that I had to use PLA to print this because anytime I did any other materials such as ASA or PETG, it would always split along the layer lines right here. So that was interesting. So the reason I moved from a 3/4 inch OD shaft to a 1-inch OD shaft is so that I could fit a GX12 connector through here. Yeah, so these guys. And the only reason I used this connector is because the sensor I bought already had this connector on it and I didn't want to disassemble this and rewire it. It's possible, but it would just be extra work and nothing I wanted to deal with. We have our slip ring here and a little bit of extra wire loom just to mitigate any wire rub. Peel the wire loom back and take the wire loom off. Yeah, we got the Ethernet line here, which goes through the slip ring and into the Raspberry Pi. You got your power ground, your 2 GPS signals here. We're not actually using GPS on this, but we use the PPS timing for it with a real-time clock to get proper timing between all of the individual systems, such as the IMU, the Velodyne points, and the encoder data. Like I said, the reason I chose this is because it will slide right through the shaft. Pop that through, pull it through, and then we've got the bearing seat here for this just to drop into like that. And here's the bearing cap. So use the bearing cap to locate the bearings inside this. You can move without it, but pop this in the right way. Boom, and there we go. Now we've got rotation. So I'm going to take this apart, put this back on, put this back over the wires, keep them nice and protected. Oh, here's something I didn't add. So I soldered each of the wires into the back of this and then just filled it full of hot glue to keep anything from coming loose because solder joints can crack easily. It's not the prettiest, but it gets the job done. We're going to slide this back through here. Boom, pull that through, push it through, drop that there, take our bearing cap, pop that there, pop these socket head bolts back in. Boom. So now we've got rotation. Then we can take this, reconnect the sensor. So, and the rest of this just kind of hangs here. I designed in a few spots to hold the wire for a little bit of wiring retainment, but could make this prettier, but it works. It works for now. Now here we've got our motor, the 4015 motor with 3D printed bearing. So the CAD model they provided for this motor didn't quite match up, or at least the drillings didn't match up perfectly. So I've got one hole that couldn't quite fill with the screw, and it works the way it is, so I didn't fix it. Same for here. So these didn't quite line up either, but I've got 2 bolts in it and it's pretty strong. It's not going anywhere. This would drop into here. I've got space where you can do some belt tension adjustment, which is really great. I also have on the bottom designed in where it can capture the nuts, so it's a little bit easier to install. This is our encoder plug. pop that there. And then we have our motor power right there. So we can pop that there. Oh, actually, we've got to take this back apart because I didn't put the belt on it. So give me just a second.
5 minutes later.
Alright, we're back. Got the belt installed, motor there. Use the same bolts that I used for the bearing cap. Cut them a bit short with a Sawzall, just so it fits better. So we have this bit of space here, some belt tensioning. So we'll slide it as close as we can here. Pop the belt back on. It's a 200 millimeter belt. So now we can push this out, get some tension on it, tighten it. There we go. Probably a little too much tension there. That should work. You know, all this stuff is 3D printed, and this motor can generate a bit of heat. And you've got this constant tension on it. This right here has already started to deflect a good bit. So with the old motor I had, it would get a whole lot warmer than this, and I initially printed it out of PLA. I was constantly replacing these just due to them deforming so much from the heat. We got all this for power supply. Really needs to be cleaned up, but we're just trying to get a proof of concept here for now. Got another red wire somewhere. There we go. Like that. Boom. I've been using this 12-volt lithium-ion battery to power just about everything. Well, it's actually powering everything except for the TNC. I've still just been using this portable power bank for that because there's lots of times where I need to plug in the TNC to my laptop to make some firmware changes for either PID tuning, encoder data, or anything related to the rotation assembly current function. Plug this up, you can turn the switch on, plug this up, and that should start to spin in just a few seconds. Initialization, and boom, there it goes. So right now it's set to about, I think right at 20 RPM with the LIDAR recording at about 15 Hertz. Turn it off, on, simple switch. I added the switch because with all the testing I do, I leave everything powered up and I don't need this constantly spinning. And this makes a lot of noise and it gets quite annoying. I haven't quite figured out how to get rid of all that noise yet. As far as the powertrain for the system, we've got a 200 millimeter 2GT 6 millimeter wide belt and a 60 tooth gear here and a 20 tooth gear here, which gives us a 3-to-1 gear ratio. And I found that works decent. Moving on to this, we have this simple carrier board right here. It breaks out a few of the connectors and holds the TNC40. The reason I did that is because this thing isn't easy to place. It's so small, which I guess is why it's called a TNC. And I didn't want to damage it just by throwing it inside of this box. So this helps keep it a little bit cleaner, reduces the amount of wires slightly. We've got a couple connectors broken out. This connector here connects to the Raspberry Pi 5 and transmits the encoder data. So we've got that. We've got this one, which actually gives us, this feeds in the encoder data directly to the TNC. So then we've got the simple FOC board. The FOC board, it's got your 12-volt power and ground, which is on the switch here. Switched 12-volt power and ground. And then I've got these wires, which go to the motor that need to be cleaned up a little bit, but they still work. Get the job done. So you pop that here. Boom. And then got some double-sided tape so that we can just stick that there. Good to go. So one of the big things here is this rotational axis. Initially, what I wanted to do is have the optical center of the laser in line with the rotational axis. That would make all of the deskewing of the point cloud significantly easier. But whenever I did that, this rotational mass would be unbalanced, and that would just cause even more issues. So it's offset by about 5 millimeters, and that was as good as I could get it balanced. Don't really have any of those issues anymore. So this rotational cup is probably one of the most iterated parts. So you can see we have many different versions, from different materials to different iterations of the height. And another big issue that I ran into was without this support right here. So this sensor doesn't weigh too much. However, it does weigh enough to create a little bit of deflection of this. I spent a couple days fighting what I thought was run out issues in the shaft, which actually turned out to be just deflection of this cup here. So I added some simple supports here. It's not ideal for the wire routing, but gets the job done and helped reduce all of the issues I had there. Alright, so here I'm going to walk through the process of powering it up and doing a static scan. Gotta figure out where all the plugs are because it's an absolute mess of wires. Plug up the 12-volt battery. This will boot the Raspberry Pi, HMI, IMU, which we don't need here for a static test, but just leave it all powered up. Then you can hear the LIDAR sensor spin up as well. Then I've got separate power supply for the TNC motor controller. So we'll plug that up to this, make sure switch is on, and it will initialize and begin to spin around 20 RPM. No, that's good. Turn it off for now. We're going to wait for everything to boot up on the Pi side, which you can't see too well with the glare, but everything is running and green, good to go. So now what we're going to do, we're going to set this up vertically, just like that. Start the spin. So we've got it vertically spinning. Got the screen here, LiDARs, 16 hertz, IMU, which is not needed here, 200 hertz. Same with the encoder's 200 hertz, but I don't have that displayed on the screen. And then we've got about 200 gigs of data left to record on. So we're going to start the recording, and I'm going to hide under this table for about 2 minutes, and then we'll be done.
2 hours later.
Just finished the recording. We'll turn it off, take it inside, and start to review the recording. Usually when I have it inside, I just run it off of a power supply. Makes it a little bit easier. Plugged up to the power supply, everything will boot back up. Takes it about a minute or two for everything to initialize, and then we will get back in just a second. Everything's powered on and booted up. Next, we'll connect into the Pi 5 over SSH. Alright, so now we're going to log into the Pi 5 over SSH. That load, open folder, oh shit, wrong button. Open folder, it's going to ask for the password again. Alright, we're in. So I've got a directory where all of the RAW's bags save are right here. And here's our most recent recording. We've got IMU data, platform angle, velocity, platform velocity, and point cloud data. So we need everything except for the IMU data. That's not really needed for the static scanning, but we'll go ahead and download it to this directory where we will do our deskewing, offline deskewing. So we'll download that and check back in once this download completes. Alright, so here's where the file downloaded. Got it right here. So next up, we are going to run the ICP merge here. Let this run, and this will create a point cloud file. Takes a little bit, depending on the size. Also, for reference, this 2-minute long scan was 400 megabytes compressed, and then a little bit over a gig decompressed. It's doing its second pass now. We've got almost 21 million points. Downsample down to 13.75 million points, which is still a lot. So that was over 13 million points in 120 seconds. So let's see what it looks like. All right, there we go. So it's pretty impressive how well it works. Check out the swing hanging in the tree over here. Got a shed over here. Check the fence line. Another shed. What I think is really cool with all of this is the imperfections you can see in the ground. So I recently had a concrete truck in my backyard pour this patio, and you can see all of the indentions in the ground right here. And I mean, you can see it in person, but it just seems really exaggerated in the point cloud. Check out the grill cover, the Yeti cooler. It's pretty good. Then we got the power lines you can see as well. Then you've always got the trees. Trees always look really cool in point cloud. Go change colors. Single. So there's that. Cool thing with this is if you open up more than 2 PCDs at the same time, alright, so we've got 2 open at the same exact time, and now we have a bunch of other tools that we can use to align these. We've got F2, so we can just see this scan independently. What is this? This is this is a scan of the front of the house, while this is the back. So we don't have a lot of shared geometry here, but let's see if we can stitch it together. So we know we've got this fence line we could utilize from there, and then right here we've also got this side of the house over here we could use. So we got pick a line. I'm going to go over here. Let's say, let's pick a point here at the edge of that house. So get out. Let's hop to the other scan. So that same point on this scan should be right here. Boom. All right. So there's our first 2 points we've got. All right. Next up, it's another good shared feature. I forget where I am. Yeah, this one's a bit difficult because they're not in the same point at all. You know what? We're just going to go for it. We're going to go for that peak of that house. It's not an ideal to do 2 this close to each other, but we'll see what happens. Boom. Go back around. All right, we got a peak here. Boom. All right. Those are 2 points placed. Now I want to try one on the fence. We're just going to have to make sure we get the right spot. So good reference might be, do we have the corners? Let's see. We'll go for this corner. All right, got both scans here overlaid, which you don't really have to show either. So for that, we press I to run the iterative closest point. We'll see what happens. Do I have all 3 points? 1, 2, 3, 1, 2, 3. Oh, sorry, no. I need to press G. Press G to align 3 plus pairs. I got the other alignment tool mixed up. So now it's frozen up. Give it a few seconds to load. All right, look at that. And we have a match. So let's see, just kind of compare. Here's a good point to reference. See, it's not perfect, but it did a pretty good job. You know, you've got these 2 telephone poles which give good reference points from long distance. And let's see, check the side of the house. It's pretty decent. Yeah, a bunch of points overlaying each other. So now just from those 2 scans we have Got the entire front and side. Here we go, get the colors merged. Yeah, so check that out. You know, that's less than 5 minutes of work. That's the whole stack. Belt drive, FOC firmware, and the point cloud deskewing to put it all together. The bench test and the backyard test have all been great, although I've slightly stepped away from utilizing a SLAM algorithm and more towards static scans and point cloud deskewing. Everything's been working great, and I'm excited to get this system out into a cave and do some initial tests. I went ahead and shared the GitHub repository for the point cloud deskewing and the motor controller in the description below, so check that out if you're interested. I'm hoping to continue to document more and more of this and have all of the information out online, fully open source, eventually. It's a lot of work to put together. Hope you enjoyed. Stick around for the next one.